maybe we can go through topics and then maybe everybody can say, and maybe we can update document later or next time before the meeting.
Okay, so like I yesterday like spent some time looking on this baseline metrics, and like it's actually what is Alexi also saying, like 2G is like very slow because it's like heavily swapping, and basically it's unable like to like run majority of the tests that we have in the GPT, at least from what I saw. And actually, like from what I saw, then later looking at the memory usage on the 2G from the baseline metrics, is that we are somewhere short about like 1.5 gigabyte of the memory on like 2G. So like it seems that we need to use about 1.5 to 2G of the memory of swap to actually to run anything. And it's pretty nasty. Then I kind of spent some time with the Spring. I kind of posted the snippet that I use and applied on top of the Omnibus. But like I only got about 250 megabytes more space. So it's not really like a lot. But from the interesting sides, it actually had some very nice benefits because like application was loaded only once. All the like forking, copy and write was shared. So like then running Puma on top of that or like Sidekiq on top of that was pretty super fast. But additionally, like Sidekiq cluster like works out of the box, like with this preforking on top of Spring. So like if you would have to configure Sidekiq cluster using multiple queues, it would be like pretty instantaneous to run because it would use this parent Spring process. But also like running things like race console, they are pretty much instantaneous with the Spring preloader because all the processes loaded. So like you get a Spring console in like something, I don't know, 10 seconds basically, instead of usual like around 1 minute. So
I mean, it's interesting. Sorry, just a quick remark. It's interesting that you say it's about 200 megabytes because that seems to be in line with what our PSS readings yield, right? Because we know already that most of the memory is not shared. Most of the memory is unique to a fork process, a fork worker, at least for Puma, and only around 250 or even less than 200 to 250 megabytes are shared. I mean, this of course, yeah, depends on how many workers you run, but like in the default setup with running 2 workers.
yes, and actually like I actually have this topic, and I think it's due to, are we actually loading everything really? Is there like some code that is then being lazy loaded later that may impact like our pages being used? So I think like really the next step to figure out to do next is like somehow hook into the loading routine and print out exactly what code is being loaded in what process. Because like I mean like I'm also surprised by this like inefficiency. I was kind of expecting somewhere around like 500 megs instead of 250, but it can be like indicator of that like that we may be just loading some additional code or like initializing some objects that, or like modifying the class objects that kind of creates these a lot of copy and write pages. So I think like it's this like it's part of this story about the idle versus runtime memory, or like idle or like fully forked, maybe like even before, to actually figure out why we have so many copies being done. Because like I mean like this number is like too low for me, and I don't really I think I didn't find yet exactly why it is so low. It should be somewhere around like 500 megs. This would be like the reasonable number that I think. So I guess this is really like what I spent time on. And I'm actually like right now rerunning all my GPT against like 2G and 2G with Spring to have like the apples to apples comparison on the Prometheus, because I just want to like compare graphs directly, or like in the exact point. So once that finishes, I just want to like to continue looking probably at that Spring. Nicola, how about you?
Let me share my screen for a second. So I was working on investigating memory content. What I wanted to do, I tried to get like 3 different like memory heaps from the virtual machine that I was testing, and in parallel I was running the actual GPT performance test on that machine. So I took 3 different snapshots using rbtrace, and then I like these are the steps how I did it against Puma worker, and then I used the script that will like compare those 3 snapshots and remove the common objects from like first and remove the missing objects from the third one. And then I was hoping to get some clear, like the goal was to get only the long lasting objects like that live, like that will be not cleared, like to detect the strings, symbols, or different objects that will like stay forever or stay persisted in memory. But I'm not sure that I understand these results, and I repeated this 2 or 3 times just to be sure, and every time I got different results, which is maybe okayish. But I'm not sure. I don't see any clear like places where these like leaked objects live. I was hoping to get more clear results. In the end, I also ran this for the Sidekiq worker as well, but again, I'm not sure about the results.
So
what does leak mean exactly in this case?
This is just the script like that is printing. So the memory dump looks really unreadable. Like there are a lot of small JSON lines that contains like everything that was in the memory. And I use this script that I found on the internet that is just comparing the 3 different like dumps and keeping only the common objects that existed like and stayed. Like it does some combination, some smart combination
so
of those
you
3,
just look
and
at
then it just
points in
leaves
time.
the objects that like lasted from first to the third one.
Okay, so that's not a leak, right? That just means it's a long-lived object.
Yes, that's true.
Okay.
Just the wording is like that. Yeah, I agree. It's not
so like
actual
the total size. What is this number, like the total size?
I think it just summarized the total of those.
Why does it say 0 out of
repeated?
I'm
not really sure. I still didn't have time to like look at it like that. I will spend a little more time just to understand the results because the script is not written by me. But
okay.
Yeah. This is the description, like what was the actual goal and what this script does. But I'm still not sure like why there are some zeros, maybe like I will check. I'm not sure. And especially that there were some times where I got totally different results with many less objects than this. And I also had trouble to enable at all the arbitrary on that machine.
Did you say like you pull, what if we just pull just normal heap dumps, just to see what the actual contents of the heap are.
I
think
can
that would
upload
help.
it, but like,
yeah, that would be good.
It has 600 megabytes.
Okay. Right. Yeah, I mean that makes sense. But okay, well, if you just like put up a script or whatever you used to pull the heap dump, I think that would be useful for me as well to look at.
I did.
What
There is a snippet that I used. It's linked.
Okay,
Here is
cool.
a snippet.
Because what I wanted to look at as well is how large the Ruby heap is in comparison to how large the process heap is. Because like I think one thing that would be good to understand for us is as well, like what is the limit, like the kind of the ceiling for any of these things we look at, because there's only so much like the GC compactor can do, right? Because it only optimizes the Ruby heap. So it's
Well,
like
I
all
can
these
put
like
the
40
heap
byte
in
object
some.
slots.
Sorry. I can put the heap in some of those visualization tools. Maybe that will help somehow. If you guys think it will be beneficial.
I'm kind of thinking, because like probably Matthias, you also look at that. Like looking at the heap and like how much memory is allocated on a heap that's controlled by Ruby versus how much is malloced by the C.
Yes, exactly. That's what I mean. Yeah.
If this is something that like we can understand and like, because like heap is something that we can control, but I'm just curious, like if there is a lot of malloc, can we like recycle that somehow, like reduce that amount?
Yeah, that's what I was hoping Compaction would do. I mean, I can. Did you have more, Nicola, or should I talk about Compaction a bit?
Just one more thing. Like
Yeah,
I created a different topic, like investigate the used games. I just created an issue, and I just ran quickly this morning the derailed benchmark, because it will give you the like memory usage per gem. So this is just a list, and what I can see here is that like it seems that the maximum is 200 megabytes, and I don't see any huge gems, so I'm not also sure what to do with that, because there are also some suggestions that we should maybe group them and optimize and tweak how those gems are like included, but I was expecting to see bigger numbers here.
But does it number also include like native extensions, or does it only include the Ruby?
That's a good question. I don't know.
I'm pretty sure it's just Ruby. So it
Yeah.
counts
As far as I remember,
bytes and
just
object
Ruby.
space. So it will only ever see 40 byte entities. And also keep in mind there is a you can tweak this, right? So by default there is a threshold below which it doesn't even include a file or a gem in the total, because it has this cutoff point where if it's too small, it doesn't count it. But if you have a million small things, they will still add up to a lot of memory used, and they will never appear in these reports. So I would actually suggest to run it without the cutoff point. Like just set the cutoff point to 0 or disable it.
Good point. Yeah.
Or set it super high, right? So that nothing falls through the cracks. And then I would be curious to see, that might just be interesting to know. Are we dying like a death by 1,000 cuts because we have a lot of like really small things in memory? Or is it like a few chunky things, right? That would be nice, because then it's like usually easier to get rid of one and like say, okay, this is how much we gain. But it's usually way harder to fix like the lots of small stuff going on.
Yeah.
Also, I'm not sure if you saw, because I posted it in a different issue, I think a while ago. I think one lead could be here, all the GraphQL stuff. When I looked at one of these reports before, it was loading a GraphQL schema into memory, which we definitely do not need in most cases, right? In fact, we only need it for the API fleet, Pumas. So we never need it on, as far as I know, we don't need it on Sidekiq. Unless Sidekiq is API, GraphQL stuff, I don't think it does. So, but that might be something to look at. So this schema file, there's a schema file it loads, which was 15 megabytes when I looked at it.
But also like it's like in the Sidekiq we don't need as well like loading the whole API package that we have for the grape. we probably don't need to load the controllers as well, because they are never gonna be called. So I guess like this kind of selectiveness of loading parts of the application, like we actually, I think, load everything right now in each context. So there is no selectiveness there. So I think like GraphQL is probably something like the biggest offender, but I'm just kind of curious as well, like the API package, like in the GitLab, how much memory it uses? Is it like, how big is that? Is API plus GraphQL and things like that? How much memory is that using? Because like if it's using, let's say, together 50 megabytes, this is 50 megabytes that we can save from the Sidekiq process, basically.
Any idea how to measure that?
I have no idea. The question is like, how does the derived benchmark measure the gems? How it knows how much the
It uses memory profiler. And I think memory profiler only ever looks at object space.
So maybe like following the same pattern, trying to measure like the API module, like with all the objects and everything, how much memory it uses. Or maybe this derived benchmark has some way. Maybe it can give you like the memory usage per file or something like that, that you could then just group and like provide like the given path how much memory it's using.
That makes sense. Yeah. Also, I know that memory profile, I think actually that Derailed is using the actual memory profiler that we already use as a gem. So maybe I can wrap around the GraphQL base model or Grape API to see, because it lists the results looks really nice because it's breaking it in like number of size with the file, with the classes, with the objects and everything else. So I think that this can be useful, but I will
also
need to
another thing, when using memory profiler, I would focus on, it's not visible in this derailed report, but maybe just run it manually. I think we should focus on what it calls retained memory, which is the stuff that is long-lived and will actually stick around, because there's also, it will also report things like objects that are only allocated in a single method call, and that's probably not useful to look at. Yeah, that's true. That's true. But the result contains also retained memories, so that's fine. Cool. I will stop sharing. Cool. I can go next. I'm gonna share my screen as well. Sorry, Matthias, before you start, related to these memory dumps, what should we do? Should we do something more about it, except explaining those numbers? What do you mean?
I think, like, from what I heard, I think this idea, like grouping them by file, may be interesting, but I'm not sure that, like, grouping them by file is easy and possible, because file is a weird, like, unit of information. Like, file could contain many classes, right?
I think there's other ways to group
I just keep hearing it from Camille that it would be nice to group it by file. I'm curious, like, do you want to group all by
the
file?
idea is that usually in Ruby or Rails, you have one file per class, right? So, the file would give you an indication of how large is the memory footprint of that class. It's a proxy for it. It's not exact. But,
Yes, so actually like our pattern is like really that like we have basically most of the time single class per file, which is also like auto-loaded. So it like it needs to like have the correct file path to be resolved to the given module and the given class.
Okay, that's fair because of the loading. Yeah, file means a lot also.
Cool. So I'm going to talk about compaction. Is everyone familiar with heap compaction, or should I talk quickly about what it does and how it works?
Please talk, because I'm not sure. Like, I have all the context.
Right.
Yeah.
So I think the main point here is to recall that the process heap in a Ruby app actually consists of two parts, right? So there is the overall memory that the process claims, which is allocated through malloc, right, from the operating system, and then within that overall space sits the Ruby heap, which is managed by the Ruby VM and managed by the garbage collector. So these are not the same. So one is the subset of another. And the only thing that happens in the Ruby heap is keeping track of which objects are alive or can be recycled, right? And that happens in these 40 byte object slots. So a Ruby object is never larger than 40 bytes on the Ruby heap. If it is larger, the GC actually needs to, or the Ruby runtime needs to claim extra memory from the operating system heap, which will then live outside of that Ruby heap space. So yeah, and like one of the problems was prior to having compaction is that, oh, and I should add, like all these slots, so if you need extra memory, if the Ruby runtime needs extra memory, it doesn't malloc individual slots, right? So it goes to the operating system and mallocs these blocks of 16 kilobytes, which is called a page, and that's how they group. All these slots are grouped into pages. That's also what you see in the GC stats, right? When it tells you the heap length, that's actually the number of page objects it maintains. It's just an array, like a linked list of heap pages. So, so that being said, yeah. So one of the main problems that we have or had is that there's like runaway memory problem where, because the Ruby heap gets fragmented over time because you keep like releasing and allocating new object slots within these pages. At some point, so you will keep, like Ruby will keep allocating new pages from the operating system as it runs out of space, and it can only release such a page back to the memory. It can only like deallocate, like free that physical page and give it back to the operating system when it's entirely free. So, and that's why fragmentation is a problem, because it makes it much less likely for any of these pages to ever be completely free. So there can be no single object be allocated in anymore, right? So that's why typically Ruby memory only grows over time, right? Yeah, so in fragmentation, defragmentation or compaction, it's basically defragging your memory. The idea is that you cluster all you basically move all these object slots around from one heap page to another so that you have only full heap or mostly full heap pages, and then a bunch of free ones so that Ruby can release that memory and return it back to the operating system. So that's the main idea of compaction. And there's limitations to this, right? So first of all, it's because, yeah, you need to actually be able to compact it enough so that enough pages are releasable, right? But also there are certain cases in which you cannot move an object around. A good example for this is a native code, right? So if there's any kind of reference from C code into a Ruby object, if it will hold an address, a pointer, right, to that object on the Ruby heap. And if the native extension doesn't know what the GC does and vice versa, right? So then there can be no consensus by default. So you can't always like move these objects around. So there's some limits to this. And like, so I wanted to get first a better idea of like how our heap looks like. And I was only partially successful with this because Aaron Patterson, he wrote this awesome tool called heapfrag, which does not work very well, unfortunately, but it's really awesome. Like it will take, it starts a Unix socket, Unix domain socket, and it will, so it runs so it runs a process on which it receives a, heap report. I actually don't know what that means. I didn't look actually what it looks like when it's pushing out that data, but it reads from that socket and then it plots it as an OpenGL program in this like separate window. And so basically every line, I think every vertical line here is a page, and every, this actually confused me because in the talk that he gave, he used different colors. So I think like black means it is it's a free object. Red means it's not movable, maybe because it's pinned. And then I suspect green means it's used, I suspect. I might be confusing black and green here. I'm not totally sure. It's just not very well documented either. But yeah, so I tried to use that, and it was hard because like more often than not, it just crashed on me. And it took a very long time to produce this data. But this is how it showed. This is actually, I ran this in the console. I didn't run this on Puma. It didn't even work in running in Puma, but this is from just firing up rake console. I thought that would be, at least it is a kind of a proxy, right? Because it still does, it still loads like the application in memory and stuff. So this is what it looks like. And I think red means these are all memory slots that can't be moved, which surprised me because it's like mostly red. Yeah, I don't know, like this, it doesn't look right to me. I don't know why. I have to spend a bit more time into understanding like when an object slot cannot be moved. Like pinning is one reason for this, but there might be other reasons. So I just moved on into looking like how much could we actually save in terms of memory. So my first intuition was, and now I'm looking at Puma, not like the console or whatever. So my first intuition was just before we fork, it might be useful to run a compaction. So actually, I forgot to mention, GC compaction is not a thing you get automatically. It's like, I really recommend watching this talk. It's really funny as well. So basically, Aaron Patterson, he basically said, like at first, like we merged this into the Ruby mainline, and no one even reviewed that code. It's like, it was like almost unreviewable because it was very complicated, and yeah, kind of, yeah, it was really hard. It took him 3 years to finish this because there was so many edge cases to look after. So it's like, it's not documented at all. Like if you look at the, I mean, I found his talks and stuff, but so this is, so you would have to go read the C code if you want to really understand what it does. He explained the algorithm a bit behind it, which was really easy to follow. So that's good. But I don't even fully understand if it runs synchronously or asynchronously. I think it runs synchronously. And it was quite fast when I ran it as well. Fast enough to do it like as a one-off thing, probably not on every request, right? But just before you fork. So because if we start with a more compact, like a more like cleaned up Ruby object space layout before we fork, then the expectation would be this is good for copy and write behavior, right? Because then you have all the pages together neatly in those pages that will likely not change. That said, I did this and I saw almost no impact. So I'm kind of like halfway through this, but there's two ways to look at it, I guess. Like one is the actual total figure in bytes, which I hope would improve based on the assumption that if we have a more compact memory layout and if we actually can free up entire pages, then Ruby would be able to release these back to the operating system. And it doesn't look like it does. So these are two, I just pulled memory before and after we forked with and without compaction. There's just no difference. Like there's no difference in RSS used. There is some difference in the, but I'm never sure like how much this is also due to like comparing it across runs. I sometimes see fluctuations of like tens of megabytes, right? So like some of these might just be statistical like fluctuations. So there was a little bit of difference in USF. Yeah, sorry.
I think like if page is released to the system, it's actually like configured differently with the end variable. So what you may really want to look at is like how many pages are considered free from the GC stat point of view.
Yeah, that's what I'm looking at right now. I'm not done with that yet.
Because like USS, PSS, RSS will not give you like very conclusive information unless you tune how aggressive Ruby should be with releasing pages.
But that's like, I mean, we need to keep the final goal here in mind, right? I mean, because if the Ruby heap has more available slots, that's fine as well. But if like,
I mean, but like you are looking at the outcome, but there is like this middle step that like you are unsure if the page is free or not free, and if the page is free, then like you have some chance of like releasing this page. So you may look exactly how much of the difference is like this middle to the outcome point, because like this can show you like that nothing good is happening, but in fact it's happening, just you need to tune some other parameters to actually to.
That might be true. Yeah, I'm not sure what those parameters would be, but I don't think you need to tell Ruby to release free pages. I think it does that just by default, right? I mean, that's the garbage collector's job. So I think the final outcome here should be to reduce the memory use of the application, right? And so far, I'm just not seeing that, like it not in any meaningful way.
It depends. It depends because like memory allocation is pretty expensive, and in most cases, it's actually systems are configured to not release memory because it's expensive to allocate new pages. So our configuration can be very conservative on like retaining pages, even though they could be free.
And is it something I need to configure the GC to do, or
yes,
where?
Yes, I'm actually looking for these parameters for you.
Oh, cool. All right, that's interesting. Yeah.
But like the releasing pages to the memory is really like last resort.
Yeah. So also keep in mind, like this is just after the worker started, but the application hasn't done anything yet. So I also wanted to see what happens going forward, because one thing I thought I was hoping to see was that maybe because the GC keeps this internal, it's not a constant, but this internal parameter where it keeps track of, it tries to predict how the memory needs of the application in the future, just based on past behavior. So it tracks this size in bytes of how much malloc should actually claim at once. I think I said earlier, like it claims individual heap pages. I don't think that's true. I think it actually claims a bunch of them based on this malloc increase byte size. There's like a GC step, like this malloc increase bytes here. So those are the chunks of memory it will claim simultaneously, and it will increase this as your memory needs grow. So this can contribute to like runaway memory problems. Like if you load like a 1 GB file into memory, right, then the GC will take notice and it will say, oh, like your memory consumption needs are very high. So it will increase this value so that next time it asks for, because what you said, Camille, because it's an expensive operation comparatively, the next time it will ask for like twice that or something like that, some multiple of this, to not have to go back so often to alloc new pages. But yeah, oh, sorry, you had a question, Alexei?
No, you answered that already. I wanted to ask, did you run some pressure on the memory before
measuring? Okay, so yeah,
because
so
it
what
would
I did is
really different.
I did a full page load of the project page. Yeah, just to like give it like so that it has something to do. And again, this might just be a normal fluctuation, but like in the variant I ran in this experiment that used compaction, it actually was consuming more memory afterwards, at least like according to the RSS reading. So I don't know, I might have to run this a few more times and see, like, because this can fluctuate so much, like it might not be meaningful. But 200 megabytes seems to be quite a lot. But yeah, I also, I'm now looking into the GC stats, which are definitely interesting. And you can actually see, so I'm not done looking at this yet, but you can actually see the differences here that are kind of obvious, like considering that you did a compaction, the compaction count went up from 0 to 1. I think this should actually answer my question around, does this run synchronously? So I suppose it does, right? Because I just took the snapshot before and after calling GC compact. And also you can see how it rearranged. So this heap sorted length, the way I understand it is that's the length of the page array that the GC keeps. It's just a linked list of pages. So I think you need to multiply this by the page size to get the actual memory that it has so far been allocated. And the allocated pages, this will never be larger than this, right? So this will be smaller or equal to this. So these are the pages that are actually allocated right now. The allocatable pages is the difference in between that. So this basically means this is your headspace or your that's not the right word, right? Like, I think like the leg room, right? That you have before you have to call malloc again, I think is what this means. And so after this looks like it's been aligned, so it actually allocated the same amount of pages it had and this actually went down. So it looks like it released a bunch, right? So it released what is that, 1,200 pages or so, which is not that much in terms of raw memory megabytes, right? But yeah, so this kind of like got aligned. I don't know what you want to call that. Yeah, I don't know. I haven't looked into this further than this, but yeah, that's what I have so far. So yeah, I don't know. Like maybe there's also other like points in time where we might want to run a compaction. So like someone suggested in here, well, I didn't suggest compact, but like to maybe we want to like GC at certain points in time, like after running the worker. I don't know if that makes sense, to be honest, but he mentioned this is something we could look at. So overall, I don't suspect this is going to have a big impact, but I still think it's yeah, can make sense to look into it.
GC is usually quite time consuming, so I'm not sure like if executing after that, like each individual worker would be.
Well, but not compared to a Sidekiq worker actually executing. That's a fairly small chunk of time, right? I mean, a major GC cycle is in the order of milliseconds. So I think our average Sidekiq job runs more on the order of seconds. I think. I might be wrong. We can look into it.
I'm not sure. Like probably you would have, but like if like the Sidekiq, if some Sidekiq jobs take 10 milliseconds and like we take 5 milliseconds to execute GC, and given that this like Sidekiq can execute concurrently, may have side effects basically.
Yeah, I don't know. Yeah, it's also, I think there's like way more impactful things we can do with Sidekiq than running the GC, triggering the GC. Because I think one thing we should definitely do this week, maybe I can pick that up after this, is to look into, I don't know if that collides with what you're doing, Camille, but we looked at the memory sharing problem with Sidekiq, right?
I'm kind of wondering, like, because there are like this bunch of the env params, maybe there are some better settings to make GC more aggressive to execute, and maybe they would be better if you run them in the memory constrained environments, like to have like to allocate less amount of the slots, to allocate less amount of the pages in the single run. Because right now, I guess like the default settings could be that we want to allocate a lot of space, to have a lot of headroom at each given moment. So maybe it's like a mix, like compacting plus different settings on how much data you may be, how much slots, pages you may be pre-allocating in the single go. And maybe this is like a bunch of the n variables to make this runtime memory growth to be smaller.
I don't know how much, like, yeah, I need to, I didn't know the GC in Ruby was like configurable to that extent. I actually didn't look at this. Maybe I should do that. If you have like any links to docs, if you can let me know.
I link in the doc like n variables, some of them, not all of them, to configure GC. There are also, I believe, additional ones to jmalloc that you may want to check out. But probably this is like your first try, like trying to play with these ratios, amount of the slots, and maybe there are some good configuration that would make it less aggressive. I mean, that would make it more aggressive, but it would pre-allocate less amount of the memory. So it would be more compact by design.
Right. Yeah, I also like noticed that if you call it explicitly, you can also at least ask it to also do a sweep. I think usually it separates the mark and the sweep phase. But yeah, I can look into this stuff a bit more. I think I would like to do that separately from compaction, because I don't want to mix too many different things into, like, because like I want to make sure that we know at the end what causes, cause and effect. Like if you change too many variables at once, it's not really clear like what actually had an impact here or not.
So I actually have like this suggestion as well. Like maybe as part of the application startup, this is like one of the trends also in the Puma with Nokoyashi fork, I guess, that it like does GC before forking. But maybe like we should kind of control this GC to happen like when application is fully initialized, like to perform this like full GC cycle to release them like the pages that maybe not needed, and then like kind of proceed to starting application. Maybe like as the last step, adding GC in the initializer on these different lifecycle events to kind of like perform a full GC sweep and like full compaction that we can maybe do to kind of start the process like with the least amount of the memory being used.
So my understanding is that a compaction includes actually two full major GC cycles right now. Compaction triggers a full GC before compacting and after. So just by calling compact. It sounds like this was done for simplicity and they are trying to get rid of that in the future, but currently it should already do that, but I don't know, I can throw in an extra GC start to see if that makes any difference. Yeah, that's all I had.
Okay, let me share my screen. So yeah, I was experimenting in Puma in single mode. To start with, I just found that even running on small benchmark, like 5 seconds to RPS, for me gives some failures on 4 gigs machine. So that's something I think to keep in mind, at least for my stance, because yeah, it's kind of weird that even for gig machine fails some test. I didn't look deep down into that. Maybe this intended, or maybe this in deny list by grant, but I will look into it. So I put some instruction how to start Puma in a single mode. So we basically put worker processes to 0, and based on the Puma code, it interpreted as not clustered. But we also have this validator, which raises an exception if running in single mode. And here I have a question for Camille. Camille, do you know, maybe do you remember some of the issues, possible issues that could come with that? Because I see that benchmarks are passing, but what I currently see is that probably memory killer won't work, right? Because it currently...
Three problems that are associated with that. Like first one, memory killer will not work because there is no thing to kill.
Yeah.
Second, Prometheus scraping matrix
yes.
in native C, so it will create contention running in the single if you scrape matrix and there is a lot of matrix. Basically, we stop execution of everything that is Ruby. And the third problem, the graceful shutdown, so that you allow to process requests while returning health check failure, will also not work in the single mode because there is no proper hook for that.
Okay.
So these are 3 major reasons why single mode is not functioning today properly. I mean, memory killer probably not being like the biggest issue, matrix being quite significant because it's actually blocking Ruby, and graceful shutdown affecting 0 downtime deployments basically if you use health checks.
Okay.
These are the reasons why we don't allow single mode today.
Okay, but if we still hack it and run it, I found these results. So quite interesting that 4 gigs have failed in a single mode at some tests, and compared to 4 gigs in clustered mode, actually single mode failed in more tests than clustered mode. I didn't look yet deep down into particular differences, but what I looked at is memory utilization in clustered mode is close to 1. So it tries on 4 gig instance, this is the red one. It tries to utilize all memory as far as I see, while clustered mode, while single mode sits at 0.8. So now for me, the question is it like a good memory utilization? So is it utilizes and could do more because of this utilization, or is it utilizes more and just wasting it, let's say, for, let's say, supporting the clustering mechanism? So that's, I'm not sure.
So I'm kind of thinking that like in the cluster mode, you kind of losing some of the memory because of the copy on write being not so effective. In the single mode, you have only single process. So probably you're saving something like 100 to 300 or 400 max of just running in the single mode, that you have just single process basically, and like you have very good memory utilization then. So I think like your result is expected, what you are seeing, that single mode is more memory efficient, but also it's slower because some of our testing benchmarks, they are CPU bound very heavily on the Ruby. So it means that you actually cutting significantly the capacity of running in the single mode because you can only use the single CPU core because of the Ruby GBL. So I guess like my thinking right now is like, it's kind of expected like what you are seeing. And it aligns like with also my understanding that like single mode is gonna be more efficient, but it's gonna be more memory efficient because you don't really lose copy on write pages, but it's gonna be less performant because you are at most using one CPU versus two CPUs that you may be using if running in the worker mode. So
Okay, so I have a couple of questions. So how could I check that this difference is actually like because of copy of write pages? So where should I look at? Like,
I don't know. It's about figuring out as part of the process,
okay,
like why.
Alexei, that's why we track USS PSS metrics, right? They should be available. We track it for every GitLab installation.
okay, I will look at. And so, I mean, since results are expected, so here I think we should decide if we're going to proceed with investigating single mode. I wonder, like, are we going to overcome these difficulties, or are they like showstoppers and we are not going to proceed with it because it's too much trouble to fix them for a possible gain?
I'm kind of thinking like that memory killer is probably not a big problem. The other ones are to overcome if you would have to. So I guess like my question is really like, if you would run Puma in the single mode, how much gain it give us?
Okay, I will try
because it can be like a good trade-off. Like if you run 2G instance, you already probably run like with two CPUs. So maybe the single mode is just good enough to run basically in this 2G. But the question is like how much benefit it gives us in terms of the memory. So like the question of Matthias, like you can use SMAN, the tool, to check like USS, PSS, RSS, PSS being proportional set of the memory.
There's Prometheus metrics as well. You can use.
And there is also like the Prometheus metric. So you can like calculate the total memory used by all Puma processes and compare like the total amount of the memory in the PSS by all Puma processes in the single versus cluster mode, and like estimate how much savings it brings us.
Okay, but it also comes with worse results. So I wonder how we should proceed with this. So where lies the, let's say, borderline and what is tolerable? Because as you could see, like in single mode, some specs are failing, but I mean, not much. You see like second more here, second more there, but do we have any opinion like when to call this an issue and when to call this like something?
My opinion is like that we are running 20 requests for 1K architecture. So we are running pretty extensive like load on this like presumed 2G or like this small instance. So I guess it's it's about like really defining the capacity. If you would run in the single mode, how much capacity it offers and like what is designed for. Maybe it's not for 1K architecture, but it's maybe for 100 type architecture or something like that, where like you don't run 20 requests per second, but you run maybe 10 requests per second and it's fine. It's within our limits. So I guess like the results, I think it's worth understanding why these results are worse, and in some cases why they are maybe similar. But usually it's basically due to Ruby GVL and single thread problem of the running in the Ruby. But maybe it's not really the problem if you run on this small instance, because like 2G will never be a big instance. It's not it will not be able to handle maybe 1K users. So maybe it's designed for a much smaller type of the installation as well.
Yeah, we actually have a new reference architecture for less than 500 users. I think they just added that recently. Maybe have a look at that. Maybe there's some
I run it,
expectations around
5K to RPS, I think. It's something like this. So yeah, okay. So my next steps would be, I think, to actually like explain the difference in PSS, trying to like describe it in a clean way via metrics and see different, let's say, request pressure, and see maybe in 10 requests per second, it would be operating nice in a single mode. And then probably I try to look if I will be able to into these issues and try to shortly describe them, what it comes with these issues. So that's it.
Yes, probably like the biggest issue in the single mode is the Prometheus matrix. It would have to be somehow rewritten to something different, but I guess like it would not be really a super challenging thing to do. I guess it's really about like the amount of the memory saving it gives us if you would run that in the single mode.
Okay.
So actually, like we have pretty interesting investigations from yesterday. So what we are looking at today, I personally want to continue like with this Spring and understanding like loading of the dependencies to see if I can make the maybe this preloading approach be more efficient. I just want to figure out if I can like preload significantly more to have like much more memory utilization. And I will probably try to use Alexi Puma single mode to see if it actually helps with reducing further, because maybe it brings like 200, 300, 500 more space. So it would already give a lot of more headroom, and maybe I would be able to finish most of the tests on the 2G. So I guess this would be really my focus today. I want to basically continue with the Spring, figure out like the ordering of the loading, if there is loading happening after the forking, I want to get rid of that, use Alexi Puma single if it's possible, and see like how far it gives me like the room for the.
Okay,
Yeah.
I set my focus. So I will probably try to wrap up the difference and to like look into single mode restrictions. So time box it.
Yeah, I'll continue to look into compaction, wrap that up. And yeah, I want to spend some time understanding the sizing of the heap, like what I said earlier, like how large is the Ruby heap versus the whole process memory being claimed.
Okay. I will try to understand better the results that I got and to understand better the script and the numbers that is showing. And maybe I'll try to analyze a little bit more, since I already get, I think, 15 different heaps snapshots. So I will maybe take a look and see any other means to analyze this heap snapshot, and then I will probably continue looking at those gems and maybe run some memory profiler against GraphQL or something like that. I'm not sure which topic this is related directly, but I guess it also goes with the gem sizes and everything else.
I guess, Nicola, like you can create a new topic if you
Yeah.
want to this be as specific as possible. So that's it. Any other questions, suggestions?
All good?
No, maybe later,
Yeah.
like somewhere in the middle of the day. Yeah.
Okay, so thank
Cool.
you.
Thanks,
Good
everyone.
luck.
Thank you. Thank
Bye-bye.
you.
Thank you.
See you soon. Yeah.
See ya.